Hello, I'm Mr. Craig and I wish to discuss bonding types with these different types of problems here. Now I'm only going to work out the first three types of problems and hopefully you'll understand why I'm only working the first three out. So here we have the worksheet and it asks us to determine whether the molecule or the compound is ionic, and I'm talking about the types of bonds, so the bonds between the atoms, whether it's an ionic bond, a polar covalent bond, or a nonpolar covalent bond. And so once we've done that, then we will determine whether or not, if it is a polar covalent or an ionic bond, we're going to assign some charges to it. And recall that we discussed the partial charges, that if we have a polar covalent bond, that means that they're sharing the electrons, but they're not sharing those electrons equally. So one of the atoms, whichever one has a higher electronegative value, will have the greater attraction for those shared electrons, causing that element to be more negative. In other words, there's a part of a negative charge associated with it. Unlike an ionic compound where the metal says, here nonmetal, I'm giving you my electron or electrons, therefore that metal now has a full-blown positive charge of some sort, and the nonmetal has a full-blown negative charge. Now what I mean by full-blown is it's not a partial, or it's not a part of a charge. And then the last one, if it's a nonpolar covalent bond, that means that they're sharing those electrons equally, which means that neither of those atoms has a greater possession of those electrons, and there's no charges or partial charges associated with that. So the first thing that we want to do whenever we look at a compound is we want to find the difference in the electronegative values. Now you do not have to memorize the electronegative values, however you do need to be able to find them. And in your notes I gave you the electronegative values, and notice that there are no values for the noble gases. If there's going to be a noble gas, I'll make sure that you have that value in front of you. Look at the trend as we move left to right along the periodic table, that the value, the electronegative value, does increase. And as you go down a column, it should get relatively smaller. But there are a few exceptions. But again, you don't have to memorize this table, just make sure that you can utilize this table. Alright, so let's take a look at our first one. Now, you will see some polyatomics thrown in here every once in a while. And again, a lot of the polyatomics are made up of nonmetal with nonmetal. We are not doing anything with the bracket or the charges yet. Later on when we start drawing Lewis structures, these brackets and charges will have significance. But right now, just ignore it. I just wanted to make sure that it was on there so that when you see that later on, you're like, well, why wasn't that bracket around the OH earlier? Because it does have a charge. It is a polyatomic. Alright, so the first thing that we want to do is we want to find the difference in the electronegative value. So what that means is we want to take the absolute value. So again, you don't have to memorize these values, but you have to be able to find them. So oxygen has an electronegative value of 3.5. Hydrogen has an electronegative value of 2.1. So what that means is I'm going to take the difference of 3.5 and 2.1. Now, sometimes this value will turn up to be negative. If it is, then what we want to do is just simply take the absolute value of that. So what I'm doing, and what I want you to show, is actually I'm going to write this a little bit smaller for you, is I want you to write, okay, I have my oxygen here, and I have my hydrogen here. My electronegative value for the oxygen was 3.5, and my hydrogen was 2.1. The difference in that, if you need a calculator, hopefully you don't, but the difference in this is 1.4. So again, if we would have had these things flipped, then of course take the absolute value of that. But in this case, it gives us a positive value. Now, the difference in the electronegativity is 1.4. So what does that mean? Remember or recall that when we talk about the differences in the electronegativity, if it has a difference of 0, in other words, both of the elements have the same electronegative value, that means that they have no greater attraction for those shared electrons. Therefore, this is going to be a nonpolar covalent bond. Okay? We can kind of abbreviate this to be an NPC. Now, remember, there's two components to this. When you see the word covalent, hopefully when you see the word covalent from this day forward or whenever you heard it the first time, the first thing you need to think about is sharing. Now when you see nonpolar covalent, that means that it's equal sharing. If it didn't have that nonpolar component on there, then polar means, or I'm sorry, if it didn't have that non-component, polar covalent means unequal sharing. So when we have a difference in the electronegativities of 0, then that means that they're sharing those electrons evenly. If you have a difference in the electronegative values, let's say of 0.1 to about 1.69, and I probably even said in class 1.7, so I'll go ahead and say 1.7. If you have a difference between these two values, then we can say that we're looking at a polar covalent bond. Okay, so again, if you're looking at if it's sharing or not, yes, they're sharing the electrons, but they're not sharing them equally. So polar covalent means that we're looking at an unequal sharing. One of the elements will have the greater attraction for those shared electrons. They're not sharing them equally. So if you were to abbreviate this, you could say that it's a PC. And then the last one, if you have a difference in the electronegativities that's 1.7 or greater, okay, now notice that, yeah, what if it's 1.7? I'll tell you here in a second. If it's 1.7 or greater, we're simply going to say that we have an ionic bond between the atoms, which in this case means that the metal is giving away its electron or its electrons to the non-metal that it happens to be with. Now hopefully you noticed something that I said there. If it's ionic, we have a metal. In these other ones, we do not have a metal present. These are non-metals with non-metals. Here, if I have an ionic compound, I have a metal present. In other words, I've got a metal that's over on the left side of the periodic table. So if you do get a difference in electronegativities that happens to be 1.7, you're like, ooh, is that polar covalent or is that ionic? Ask yourself, is there a metal in the compound? If there's a metal, and say that we have a metal in the compound and we get a difference of like 1.59, you better make that ionic. All right? So this is a generalization. Doesn't mean that it's concrete. This is just something that we can follow. So if you see a metal in the compound, don't even think twice. It's ionic. You'll never have a metal with a metal. We'll always have a metal with a non-metal or two non-metals together. All right, so I wanted to make sure that we were clear on that. All right, so getting back, since our difference is 1.4, that means that we do, our difference is between 0.1 and 1.7. We're looking at a polar covalent bond here. So that means that we have a polar covalent bond. And since that means that we have a polar covalent bond, what does that mean? Well, I need to show my oxygen and hydrogen which of these two elements has the higher electronegative value. The oxygen. Therefore, it is more negative. Anytime an element has a higher electronegative value, it is more negative. But since it's a polar covalent bond, that means that we have partial charges. All right? It kind of looks like an 8, but it's a lowercase delta. Don't worry about it. The oxygen has a partial negative. The hydrogen has a partial positive. Now, later on, we're going to get where we have more than one element. Don't worry about how many partial parts there are. We're just going to say it's partial negative or partial positive. How did I know that that was partial negative? It has a higher electronegative value. How did I know that was partial positive? Because it has a lower electronegative value. How did I know what those electronegative values were? I went to the periodic, or I went to my notes and I looked at it. You will also have this table for a quiz or a test or whenever, anytime that you need it. So it's just a matter of looking it up and saying, oh, oxygen, 3.5. Hydrogen, 2.1. Got it. All right, so let's take a look at the next one. Here we have N2. There's only one kind of non-metal in this compound. This should be super easy for you. But I still want you to show the work. So we have a nitrogen and a nitrogen. Pretty straightforward. Taking a look at the values. So nitrogen has an electronegative value of 3.0. So that means that it's 3.0 minus 3.0. And what does that equal? Very good. 0. Okay. So if it equals 0, then we're looking at a nonpolar covalent bond. which means that these electrons that are between the nitrogens are being shared equally. So this is a nonpolar covalent bond. Don't know why, there we go. So since there is no difference in electronegativities, there are no charges here. No charges, period. Since they're sharing those electrons evenly, there is no difference in sharing. And again, you may have noticed on my notes, if I can notes, it makes it kind of nice that when you look at a nonpolar covalent bond, this represents, these two black dots represent two elements. So they're sharing those electrons evenly. When you look at a polar covalent bond, the negative, or the one with the higher electronegative value, has a greater attraction for those shared electrons where the positive doesn't. And then if you're looking at an ionic compound, which we haven't done an example of yet, the metal has given the non-metal its electron or electrons. So there is absolutely no sharing, no connection, so to speak, when we look at the ionic compared to the connection or the sharing of the covalent type bonds. Nonpolar covalent, even distribution. Polar covalent, uneven distribution. Ionic, total distribution. Look at the last example. So we have HF, and when looking at it, so again I have my hydrogen and my fluorine, and my electronegative value for hydrogen, again, is 2.1. Fluorine is 4.0. So what do? I write 2.1 minus 4.0. And again, since this time it would give us a negative value, let's take the absolute value of that, and it gives us a value of 1.9. So again, 1.9 is greater than 1.7. We are looking at an ionic compound. Now, you might say to yourself, whoa, wait a minute. Hydrogen's way over here. Yeah, sometimes hydrogen acts like a metal, sometimes it acts like a non-metal. How are you going to know how it's behaving? Very good. You're going to let the electronegative difference tell you how it's behaving. So the hydrogen could be over here, it could be over here. So we're going to look at the difference in the electronegativities, because when you put hydrogen with carbon, it behaves as two non-metals. They're sharing those electrons. That's a whole different type of concept that I don't want you to get worried about just yet. So for right now, you're saying to yourself, well, hydrogen, I've known hydrogen all my life as being a non-metal. That's okay. Sometimes it acts like a metal. You'll get over it. All right, so in this case, we do have a difference of 1.9, which means that we are looking at an ionic compound. Okay? So when you're looking at an ionic compound, what this means is that the hydrogen is acting like a metal. How do I know? Because it has the lower electronegative value. I know that the higher the electronegative value, that thing is a non-metal. So what that means is hydrogen has 1 electron, and fluorine has 7 valence electrons. We know that from past stuff. So the hydrogen is going to give the fluorine 1 electron. So in this case, hydrogen is going to have a +1 charge, and fluorine is going to have a -1 charge. And that's what we did right before break. So you should still be able to balance those type of things out. All right, so what I've given you is an example of an ionic compound, a polar covalent compound, and a non-polar covalent compound. What I want you to do with the rest of these is use the differences in the electronegative values and show this work. So make sure you're showing the difference in the electronegative values. Determine whether it's ionic, polar covalent, non-polar covalent. How do you remember? If you don't remember, write these down on your sheet. Turn the paper over. You're going to have to memorize these values for the test or the quiz, or both. And then make sure that you, if it has charges, whether partial charges or full-blown charges, you have to show it. If there's no charges, I'm okay if you just write a dash in there. That indicates to me that at least you know there's no charges and you just didn't leave it blank. So put something in there. NA is okay, like not applicable there. If you want to do that, that's also okay. All right. We're going to need to be able to do this, or be able to do this type of skill for our next topic, which deals with drawing Lewis dot structures. Hope this video was helpful.